Our project is Jigsaw Unintended Bias in Toxicity Classification, detect toxicity across a diverse range of conversations. Now this computation is the second largest computation in Kaggle. It's very competitive. Now I want to explain the background a little bit. So when the conversation AI team first built the toxicity model, they found that the models incorrectly learned to associate the names of frequently attacked identities with toxicity. Models predict a high likelihood of toxicity for comments containing those identities, and even when those comments were not actually toxic. You can see from this word cloud, actually the word with largest frequency is Trump when the toxicity level is gray, is very big, and the second one is idiot. So about the datasets, the datasets from Kaggle contains 1.8 million comments in train set and 97.3k comments in test sets. The target is the toxicity level ranging from 0 to 1. It has several additional toxicity subtype attributes such as options, threat, etc. It also has several subsets about identity such as male, female, like gender attributes, Christian, Buddhist, religion attributes, and Asian, like black, white, those race attributes. So okay, then I want to introduce the methods we use to participate in this computation. So firstly, we didn't really do the data process to process the data. We only did some light cleaning, and we choose 3 models. Basically just one model is RNN, but the very first one is the simple RNN, like the very basic one. And we also choose GRU, which is a newly developed RNN with 2 gates. And then we use the most common one, LSTM. It's the 3-gated GRU. In these models, we have like 8 layers, but with very light. I think we only tokenize the data, the comments. So it's very premature, and the accuracy of this one is fairly low. So we just want to see if there's a difference between these 3 models to see the results. And for the second stage, we did some pre-process of the data. So firstly, we cleaned all the punctuations of the comments, and then we clean out the contractions, such things like I have, eight, things like that. We also format a lot of swear words. As you can see, there are a ton of different kinds of swear words you can find online, and we all replace with like one format swear words, so it's more like disciplined. Then in this model, we added identity parameters, giving the weights of the overall groups and subgroups based on the evaluation method. So this time the model is more complicated with weights. It works a lot better, especially with LSTM and GRUs, since we add more flexibilities. And here's the evaluation method of this computation. So because of the nature of this dataset, the evaluation process focuses on not only accuracy of the prediction on test dataset, but also the bias of the models. So the evaluation builds a newly developed matrix that combines several submetrics to combine overall performance with various aspects of unintended bias. So during the process, the overall performance is evaluated by ROC AUC for the full evaluation set, and the unintended bias is measured by 3 bias AUCs corresponding to 3 specific subgroup of the test set. So the first one is the background positive subgroup negative. Second one is background negative subgroup positive. And you can see from here that's the equations. So firstly, they got the generalized mean of the bias AUCs, then they plug in to they add to the overall AUCs to get the final score. Then these are results. You can see with very light pre-process of data and very immature models, I would say very easy build models. The scores not very high, and especially you can see the LSTM performs worse than GRU in this case, because LSTM, I'll explain it in the discussion part. And for the second stage, you can see LSTM actually performs the best here, but it takes more time. So actually GRU is the newest model. So GRUs usually trains faster and perform better than LSTMs on less training data. That's why in the first stage it performs better and faster than LSTMs, because we have less information, less data. But in the second stage, we add more parameters, we add weights. So in this term, LSTM actually has a better score than GRUs. That's why. And GRUs are simpler and thus easier to modify. For example, adding new gates in case of additional input to the network is just like less code in general. It's just easier. And LSTMs should in theory remember longer sequences than GRUs and outperform them in tasks requiring modeling long distance relations. That's why when we add more parameters and we have more flexibilities, LSTM outperform GRU in the second stage. There are still 2 months to go to end this computation, and we are still working on that. Recently, there's a new popular kernel that suggests using fast AI GRU to run the models, like exactly the same model. It performs better than Keras GRU. And I'm still working on that. So this is the current ranking for that. So you can see it's all very, the difference is very narrow. I think in this stage, the pre-process of data doesn't really help with the final score. It really depends on the like the parameters of the model, and I think it's probably more depends on the engine of the model. That's what I think probably the reason why fast AI performs better than Keras, because Keras is like a traditional engine. Just my personal thought. And now we ranked 416. It's not very good ranking now, but hopefully we can get it better in the next 2 months. Thank you very much.